Ever wondered how particles scatter off of a solid object in quantum mechanics? In today's video, we'll break down the phase shifts for hard sphere scattering, and in doing so, we'll break down a lot of math that is needed in other parts. In particular, what we see here is the cross-sectional scattering for several different situations with K times A, and I will link this image and its resource below. But as you see, it is quite important to us in quantum mechanics for several reasons, which we'll discuss soon. But in order to tackle this problem, we actually have to go through quite a few things. And we'll start with example 10.3, which is the quantum hard sphere scattering, and then we'll get to problem 10.6, which is what are the partial wave phase shifts delta L for hard sphere scattering that was done in example 10.3. And in the process of doing this, we'll also cover problem 10.3. So you're actually getting a 3 for 1 here, and it's actually going to be a lot of fun. But why do we care? Well, in the quantum hard sphere, it provides a simplified yet insightful model to understand how quantum particles interact with obstacles. And when we see what the potential is, it'll make sense why it's considered, quote, hard sphere. Again, not going to be that much similar to what we see in the classical side of things, but the challenge is how does this compare with the classical analog? And we'll have to definitely feel it out and see what's going on there because there is an analogy there, but it's not what you might think. At least not what I thought at first. And if you want the PDF, just please comment. I'll be happy to share it with you, or you can go to the Patreon collection and grab all the YouTube PDFs, all free for members. So get out there and go get them. And if you're curious about the world of science, please be sure to subscribe. I post educational content every week to quench your thirst for curiosity. So with this, let's jump into this video. With that. All right. Anyways, so stop number one, of course, we have to first cover the quantum hard sphere scattering case from example 10.3 from the perspective of partial wave analysis via the partial amplitudes that we had seen in a couple other problems. Okay, and then from that, we can use those to construct and find the phase shift constructions. So the potential here is that V of x is equal to infinity for any r less than the radius of the sphere. So that'd be little a. Okay, so infinity, we know it has to happen with infinities in quantum mechanics. Okay, so this is considered hard sphere, and then we're zero outside. So we have a hard disruptive figure that we have to deal with. Okay, and it gets spheres and spherical harmonics, all things like that, they work together really well. But what we realize here is that with this potential, the boundary condition needed is that the wave function at the boundary of the sphere has to be 0 because of infinity. Okay, so that makes sense. Now, if we couple this with the general solution of the wave function for these problems and these scattering problems, which is given by the summation, it all needs to equal 0. And in fact, this holds for all theta. The partial wave amplitudes here is what we need to find. And that's what's of importance to us. And to do that, we have to use an old friends that we had dealt with back in chapter 4, which is multiplying by a Legendre polynomial with the L prime and then integrating over theta, which is 0 to pi on both sides. And why we do this is because we want to exploit the orthogonality of Legendre polynomials. And again, we did that back in chapter 4. I'll go ahead and link that as well, or you can grab it from the PDF. But this, in essence, finding this AL is what problem 10.3 is trying to do. So we'll go ahead and find that result in the middle of this example, in the middle of this bigger problem. Whew, that's a lot. But let's go ahead and apply this and go ahead and find out what the orthogonality requirement is, and we'll be good to go. But note that we have 0 here, so this integral will be easy. Alright, so like I said, the right-hand side, because of that 0 due to the boundary condition, we see that that's a big fat 0 on the right-hand side again. None of these terms have anything to do with theta, so we just get the integral all with the theta terms, which is just the original Legendre polynomial and the prime polynomial. And from this one, we can go ahead and use the orthogonality requirement, which is what we see here. 2 over 2L plus 1. delta L L prime. Now, this is a summation, of course, but because of the delta, we know that we can only be, for this delta tells us that we can only be allowed for one value of L, which is namely L prime. And that's what we see here. So we don't have to worry about the summation anymore. We can drop that out. But in plugging in L prime into everything, as you see highlighted in red, we get some cancellations. This factor cancels with the denominator, good to go. Then we're left with this I and this 2 out front, but since it's equal to 0, we can divide it over and it goes away. So what we're really left with is this argument equals 0. And now again, the goal is to find the partial wave amplitude AL prime. So what we do is we take this, minus it over to the other side, and that's what we're left with. Of course, now we can divide and isolate AL prime, and we'll be good to go. Alright, so just as promised, we divide, isolate, and we're good to go. Shifting the indices from the prime to AL. That concludes problem 10.3, which is, this is the real result that we need in order to use, or in order to find what we need for the phase shift. But we'll go ahead and continue with this example since it becomes so important to us later as well, and we'll see exactly why. So once we find this partial wave amplitude, this leads us directly to the total cross-section via equation 10.27. And as you see, when we plug this in with the differential scattering, or the AL prime, or AL magnitude squared, we plug this in, we see the negative and the I go away. Since I is magnitude 1, the negative has no effect in the bracket here. So what we're really left with doing is having to go ahead and figure out what is this fraction, okay? Now, although this is the exact answer, from the book, he tells us that it's not terribly illuminating. So let's consider the case, or the limiting case, of low energy scattering. In this case, that would tell us that Ka is much less than 1. And since K is 2 pi over lambda, this amounts to saying that the wavelength is much greater than the radius of the sphere. Okay, this sounds like it would have been used in WKB, things like that, other approximation methods. So with this, if we refer back to table 4.4, we note that the spherical Neumann function, the n's, and the spherical Bessel functions, the j's, take these asymptotic forms for x much less than 0. And for us, what this means is that we're going to substitute in z, but z in this context is going to be Ka. So keep that in mind when we're using these, and as you see, because the variable is so small, much less than 1, dividing by something small leads to something big. So in actuality, we note that the Neumann functions here are much bigger than the spherical Bessel functions, so we can get rid of the spherical Bessels in relationship. How do we do this though? Well, we realize that the spherical Hankel function here, this HL to the first kind, is equal to the spherical Bessel plus the spherical Neumann function, and then of course we have the spherical Bessel up top, but in relationship between these two things, this one dominates, so we get rid of this term altogether. And that's what we see left over here in the approximation. And of course, we don't like i's in the denominator, so we rationalize it. After rationalizing, we see that we get I squared in the denominator, leaving us to a negative, and the I just comes out front. Good to go. Now, from table 4.4, we also saw what the asymptotic forms of the spherical Bessel and the spherical Neumann functions were, so we plugged those in. And the negative cancels, no big deal. And what we see is that dividing by a fraction, you multiply by the reciprocal. You see you have a 2L, L factorial. This 2L plus 1 factorial gets expanded to 2L plus 1 times 2L factorial. So we have another 2L factorial there. ZL plus 1. We can combine and simplify this pretty quickly. I and 2L plus 1 is the constant out front. All of these have a square term. Square. Good to go. And then we just combine the exponents on the z's, so we're left with 2L plus 1. So what we can now say is that the total cross-section is now approximated to 4 pi over k squared, because we can bring the k out front. No big deal. We've seen that before. And all the nitty-gritty algebras in the PDF, of course. But we have to put this into the magnitude. And so we can simplify this next. But before we do that, If you're finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content and helps grow this page where we can explore quantum and many other fields of physics. So with this, let's get back to simplifying. Alright, so after the magnitude squared is done, you know, we can go ahead and cancel that with the factor here. We now see that this is to the fourth power instead of squared. And this is when you double the exponent, you get 4L plus 2. Good to go there. But now, once we simplify it all down, we have to realize again that this Ka needs to help us here. Okay? And what we're saying is that since we're assuming Ka is much less than 1, the higher powers are negligible. In the low energy approximation, scattering is dominated by the L equals 0 term. This means that the differential cross-section is independent of theta, just as it were in the classical case. And we kind of talked on that earlier as well. And so, by plugging in L equals 0, we simplify down, and note this curious result, okay? This result is what we're curious about because it's 4 pi a squared. So although this is the extent of example 10.3, let's dive into why this result is so curious. So for the low energy hard sphere scattering, surprisingly, the scattering cross section is 4 times the geometric cross section because pi a squared is just a circle, and if I'm a BB trying to hit a sphere, all I see is the cross section of a circle, right? And we saw that back in, I think, 10.1, yeah, 10.1 is when I covered the classical case of scattering. And so the fact that this is 4 times larger is definitely curious, okay? And because of that, what we say is that this is a larger effective size, and it's characteristic of long wavelength scattering. It would be true in optics as well, Griffiths claims in the example. In a sense, these waves feel their way around the whole sphere, whereas classical particles only see the head-on cross-section, which was discovered in 10.8, equation 10.8. So, with this example done, we now have everything we need to analyze the partial phase shifts from the partial wave amplitudes, courtesy of equation 10.33 found above, which is this fella, and equation 10.46, which is from the book. So, now that we have both partial wave amplitudes and one of them has the phase shift, we can go ahead and equate these two and simplify this down. Alright, so equating the two, we see we get some cancellations immediately of k, so we can get rid of that altogether. Cool. Now what we need to do is simplify this expression and this expression. Again, what we need to do is simplify the spherical Hankel function of the first order, and we recall that that was equal to the spherical Bessel and the spherical Neumann. If we multiply by 1 in the special form of Bessel over Bessel, we can factor Bessel out of both terms and cancel the numerator. Okay, all this is doing is just fancy algebra to help us simplify later, especially in the approximation regimes. But of course, the way to actually get that much easier is to multiply by the conjugate. Again, you're multiplying by 1 in a special form, but note that the negative sign is the predominant structure here because it's the opposite sign here. And that'll help us get rid of this I as well. So let's continue with the simplification. Alright, so after distributing and all this fun stuff, what we see is that the numerator is 1 minus I, and then all the cross terms in the denominator get canceled, so we're left with 1 and another square. Okay, so if we distribute this I into this numerator, we get I plus, because two I's make a -1, negative and negative make a positive, and we're good to go. But remember the right-hand side was a collection of e to the I, delta L, and sine delta L. So what we see here is that breaking this up, splitting this up into its natural parts by breaking up the numerator, we see that this boiled down to two different equations, one with the imaginary part and one with the real part. So as you see, the color coordination now switches for the real part in purple, imaginary part in red. And from these, we can go ahead and find out what this delta L term is by splitting them up and then dividing them, and that will lead to some nice cancellations. Alright, so real quick summarizing, the real part is this, the imaginary part is this. If I take the imaginary part divided by the real part on both sides, I see I get sine one factor cancels with this over here, so I'm good to go. Then I see my numerator or denominator and denominator cancel, oh, thankfully. And what we see is that we end up with the sine delta L over cosine delta L divided by the reciprocal of the Neumann function with the spherical Bessel function. And we see that dividing by a fraction means I multiply by the reciprocal. Sine over cosine gets the tangent. So if we want the phase shift, it's the tan inverse of the spherical Bessel over the spherical Neumann. So that was a fun exploration, and it really wasn't difficult or hard, but a lot of algebra in there just to make sure everything is compact and neat and gives you all the pieces you need. This result is still pretty weird because of the ratio that we have inside, but when you do the animations that you saw in the beginning of the question, this becomes really important to help to tell you what happens with the phase insofar as what happens with different values of Ka. So very interesting, and we can observe here that although it's an asymptotic form with the spherical Bessel and Hankel, things like that, the domain restrictions on the tan inverse or arctan give us something to ponder, and we'll touch on that in a different PDF when we get to chapter 11, which is quantum dynamics. Holy! So that was fun. We covered a lot of different pieces and a lot of different parts. So thank you for watching this far. Um, Again, this example was not at all that weird to me covering it first, but then as I started typing it up and going through it, the fact that the wave tries to feel its way over the sphere is actually kind of cool. And again, you saw the scattering diagrams in the original cover. So a little more digging on this led to another rabbit hole of curiosity. So if this video is a curiosity of yours, make sure to share it with a friend who's also curious about science, and let's grow this learning community together, because this stuff is never ending. You can have a lifetime of learning and still not learn enough. So it's very important to me that we keep the learning up high and continue to provide resource for everybody, because this stuff is just fascinating, quite frankly. Um, I still have to type up a couple other things I want in a big report, so y'all be on the lookout for that. But in the meantime, I still need to thank all the supporters of this channel, the patrons, those who donated to the Buy Me a Book Club via Buy Me a Coffee. Thank you guys. It's been very helpful thus far, and I know that coming up, especially when we get to October and December, there will be a lot of other fun projects that have been done, especially in the programming sense, because it's hard to visualize what happens at this level, and animations help a lot. So that is my next big wave coming up, especially with quantum dynamics. That'll be very helpful. That being said, anything I find along the way, books, notes, and other reference materials will be found below or linked in the PDFs, so feel free to check those out. If you have any questions, please feel free to reach out. Learning is not a one-dimensional task. Several perspectives can help, so definitely don't feel weird about asking, because all of us need help at some point. As always, thank you for watching, and until next time, stay curious.